Impulse can be calculated by determining the rate of change of momentum of an object. If the mass of the object remains constant, then it can be expressed as a product of mass and the rate of change of velocity. The change in velocity is then determined by transforming the equation. Assuming we have an undamped SDOF system. Under impact load, everything happens in a split second, and the resistance from damping component just cannot be deployed on time. The resistance of the entire dynamic system is now depending on the force of stiffness and inertial force. The displacement response X when such a system is subjected to free vibration is a function of initial displacement and velocity. When the initial displacement is 0, we can simplify the expression for X. From here, we know the incremental displacement. The displacement of a general load function over a certain period of time can be determined by calculating the area under curve. Therefore, we can transform the expression of X into the following form. By simplification, Duhamel's integral for undamped system is produced. Considering a case where constant load F0 is applied suddenly to a dynamic system when time t equals to 0. The load function is F0 and it is valid all the time. Next, we substitute this function into the Duhamel's integral. Let's solve for the integration. The upper limit of the integral should remain as variable t, since we are interested to find the displacement response at any instance. From a series of operations, we express the function x in terms of static displacement amplitude and dmf. Let's replace the natural frequency in our expression with 2 pi over period. The displacement response of system is 0 when the time instance is the multiple of system period. Conversely, the response is maximum at the time of 0.5t, 1.5t, and so on. dmf of 2 denotes the displacement of system under impact load is twice as much as the displacement induced when it is subjected to static load of the same magnitude. Let's say the constant load F0 is applied only for a limited duration of time, namely from 0 to loading time Td. To analyze this case, we need to divide it into two phases. The first phase is for the time frame of 0 to Td, and the second phase is for any time beyond the time Td. F0 is applied in the first phase and no load is applied for the second. For the first phase, the general equation is basically the same as that for the constant load case for indefinite time frame. For the second phase, the effect of first phase is now the initial condition. By substituting t equals to Td into the general equation for first phase, we obtain the initial displacement for the second phase. Then, the derivative of that expression with respect to time yields the initial velocity. We have solved for the displacement response of undamped system in previous video. We now substitute the initial conditions to make it valid for the time frame of t minus Td. From a series of operations, we get to know the dmf of the loading condition. In this case, we are also expressing it in terms of the period of system. Let's plot the graph of dmf against the ratio of loading time Td to system period for various time to period ratios. From previous load case, we know the dmf is maximum when the ratio of time to period is 0.5. There is no exception for this case, where the curve corresponds with this ratio is located above the others. Within this curve, the maximum response occurs when the ratio of loading time to period is 0.5 as well. Thank you for watching. If you find this video helpful, please share it with your friends. We will see you guys soon. Goodbye.